Okay. So before we go to the Hall probe, let's see the differences first. Can you see the slide? Can you see the slide? Everyone, can you see the slide?
Yes.
Can hear me? Okay, good. Okay. So look at the differences in exam. I tell you in A2, the electric field, gravitational field, magnetic field, they are the three fields governing our universe. So they're going to ask the differences, the similarity among these three fields. But when come to magnetic field, they would like to compare with electric field, not even gravitational field. Magnetic field and electric field. Why they want to compare magnetic field electric field is the one similarity, because both exert force on charged particles. That's why they are normally compared. So what is the similarity and differences? I think majority is I think it's differences. Very difficult to say similarity. So first is force exerted on a moving charge particle, magnetic field. Electric field exerted on a both stationary or moving charge particle. The differences. Force is always perpendicular to the direction of the field. Electric field is force is parallel to the field. Force in the direction of the field. So third, force is dependent on the speed. Yes, third. Magnetic force dependent to the speed. More faster the charge move, more greater the force. Okay, and the radius become even smaller, deflect more. Okay, another one thing, when force get big, when the force is getting bigger, the radius get smaller. If when radius gets smaller, we say it deflect more or deflect less. Smaller radius means more deflection or less deflection. Another important thing you have to think. Small radius means big deflection or small deflection. Let's say one is deflect like this, another one deflect like this. One or two, which deflect more? One deflect more, right? Because of what? It has a small radius or big radius? Small radius. More smaller the radius, more greater the deflection. More greater the deflection. Remember that? Force is not dependent on the speed. Finally, magnetic field is circular path. This is a parabolic path. Okay. Okay, this question I skipped is similar. Okay, now I'm going to talk about Hall voltage. Okay, Hall voltage leads to development of Hall probe, which makes it easy to calculate the magnetic field strength. Okay, practically. Okay, a lot of wording here. Okay, let me explain to you in diagram first before we come to this wording. Okay. Okay, for this, let me show you a video to understand the Hall probe. Before that, let me show you first. Okay, let's say you have a thin slide metal sheet. Okay, carries the current. Okay, this the current is flowing this way, but the electron is going where? The electron is flowing this way, right? The electron is flowing to the downwards, correct? Current flowing this way. Okay, the electron will go straight. Okay, go straight. It moves from A to B. A to B. Okay. Okay, now let's say a magnetic field is applied. A B is applied through this surface. Okay, a magnetic field is applied through the surface. The electron is coming from A to B. What will happen to the electron?
It moves to the right. Wait, no, wait.
Okay, let me put a number. X, Y. Sorry, I can't put X, Y.
Left.
So
is it? No.
C, D, E, F lah. Okay, so where are you going to deflect? To the CD side or EF? Use your Fleming left hand rule. where the electron will deflect. The electron is coming from A to B, going A to B, electron. Magnetic field from vertically up to down. The electron which is coming out will experience a magnetic force. The magnetic force will push the electron in which direction? To CD side or EF? FBI. B is downwards. I is where? I is from B to A. Current is B to A, right? Electron is A to B. Current is B to A. Where's your force?
CD.
So CD. The force is towards CD, right? So now what happened to the electron? When it has a force to CD, the electron will what? The electron will, is it go straight?
No.
It will drift to CD. The electron will drift to CD. Okay, it will drift to CD. So the electron will drift to CD. Okay, when the electron drift to CD, the electron won't reach the B. No, the electron all will accumulate at CD because of magnetic force. Or maybe the first 10,000 electron. The first 10,000 electron comes out, it will drift to CD. Now what happens? When the electron drift to CD, the CD become positively charged or negatively charged? The CD become negatively charged, right? The CD become negatively charged. If CDH become negatively charged, mean Fe become what charge? Relative to CD. Become positively charged. Okay, now tell me, what type of field has been created now? What field has been created? What field? Electric field has been created. There is an electric field. Now one side is positively charged, another side is negatively charged. Electric field has been created. Electric field, the electric field created, is it vertical or horizontal? Is it vertical or horizontal? The electric field. The electric field is from positive to negative, right?
Yes.
The electric field is which direction? It's like horizontal this way, right? That's your electric field. Correct? The electric field is horizontal. Magnetic field, which direction? Magnetic field is vertically downwards. Electric field is horizontal. So now tell me, 10,000 electron which comes out all drift to the side, create negative charge, and the other plate was positively charged, causes electric field. Now tell me, the 10,001 electron, the following electron when it comes out, how many forces acting on that electron? Neglect the weight. Magnetic force acting where? Towards which side? CD, right? Magnetic force acting towards CD. But now you got electric force, right? Electric force acting where? Electric force acting towards CD or FE?
CD.
CD is what charge? CD is negatively charged. Right?
Yes.
Fe is positively charged. The electron attracted to the positive plate or a negative plate?
Attracted to positive.
So the electric force will be Fe or CD? The force will be towards the Fe or towards the CD? It will be towards Fe, right? The electric force due to electric. So the electron, when the 10,000, after a few electron drifted, create the electric field. Electric field. After that, the incoming electron will have a magnetic force to the CD, and the electric force will be to the Fe. Okay. When these two force balance, what will happen to this electron? Is it going to drift?
No.
So the electron will go straight. So after 10,000 electron already drift to the side, stuck at the side of CD, The 10,001 electron have chance to go straight. So you get current, get a current. Okay. But now, how many fields has been created? How many fields are acting here? Two fields, magnetic field and electric field. Which field creates which field?
The magnetic field creates the electric field.
Magnetic field created the electric field. Okay, it's a nature, it's a nature. The magnetic field create the electric field. Finally, balancing happens, the electron moves straight. We have one advantage here. Now they say, okay, because at the side CD and FE got electric field, because the plate is like sideways lah. The plate is like sideways. Sorry, the plate is like this sideways. This is your CD. This is your FE. The electric field like a parallel plate vertically. If we put a voltmeter across, get a voltage. This voltage is called Hall voltage. This is called Hall voltage. Very unique voltage. Very small. Normally it will be in millivolt. But it's a very useful voltage to measure, used to measure the magnetic field strength, which causes this voltage. So the magnetic field strength is very strong. The field, electric field required to balance must be very strong. Therefore, the whole voltage get bigger. How the whole voltage and electric field strength related? Your AS knowledge. Electric field strength, what is the formula? V over D, right? One formula. So greater the electric field strength, greater whole voltage will be greater. This is called Hall voltage. Hall, the scientists who did this experiment. So the Hall voltage discovered found to be directly proportional to the B. We're going to prove this. We're going to prove this. This derivation we have to know. That's our in few minutes time. The greater the Hall voltage means the greater the B. So from Hall voltage calculation, we can calculate the B. Okay, but try to understand the concept. In exam, they will ask which side become negatively charged, which side become positively charged, electric field which direction, magnetic field which direction. These kind of questions will come out in one structured question. Okay, any questions, guys, from here? This is called Hall voltage. Okay, I go to the description. So now read through. Maybe you can understand now. The story I told you, I elaborate to you just now. If an electric current flows through a conductor in a magnetic field, the magnetic field exerts a transverse force on the moving charge, carries which tends to push them to one side of the conductor. This is most evident in a thin flat conductor as illustrated. A buildup of charge at the sides of the conductor will balance this magnetic influence, providing a measurable voltage between the two sides of the conductor. The presence of this measurable transverse voltage is called Hall effect, and the value is called Hall voltage. Okay, Hall voltage, very important. Any part you don't understand the description? Okay, let me show you a video. Just maybe from the YouTube, maybe you got a lot. YouTube. Hall voltage. Okay, so I show you a video. You can see the video, right?
Yes.
Okay, so let me show you one. Okay, look at this. Okay, this one not that good now. Okay, this one, yeah. So the current flows. Actually, this is electron flowing. Electron flowing. So you apply a magnetic field. So use your Fleming left-hand rule. Magnetic field is to the left. Force will be upwards. So the electron will stick at the side. So then electric field is created sideways, side. So electric force balance the magnetic force. So electron will go straight. So you put a voltmeter across here, up to down, you get a whole voltage. Okay, any part you don't understand? Okay. Skip this. Okay, now what we're going to do? Another 2 slides, then we stop. Now what are we going to do? We're going to show that how old voltage proportional to B. You need to prove this. This is in your syllabus, the derivations you have to know. How old voltage proportional to B. That's what we're going to do. Okay. So you see this picture just now? So here the current is going what? Current is going from up to down. Magnetic field is applied upwards. So the electron is moving from down to up, because current up to down means electron is down to up. Okay. Use Fleming left-hand rule. Where's the force will be? The B is upwards. FBI. Show your index finger upwards. FBI. Current is to downwards. Your force, magnetic force, will be to that direction, to the left, FM. FM is to the left. So all the electron will drift to the side, causes the side edge will become negatively charged. All are negatively charged here. So therefore, the opposite side here on the right will become positively charged. All positively charged. So the electron. So the electron. This is a moving of electron. The electron. The magnetic force is to the left. The electric force Fe will be to the right. Until the force is balanced, the electron will move straight. You get a Hall voltage. Hall voltage where you put at the side. You see the Hall voltage, how the voltmeter is connected. The voltmeter is at the side. The side edges create Hall voltage. Okay. Okay. Now this slice, the thickness is D, small d. The width, the width of the slice is W. It's W. Okay. Okay. Now go for the description. The transverse voltage, Hall voltage, measure the whole probe as its origin in the magnetic field moving a charge carrier. The magnetic force we know is BQV, BQE, E is Q, V is speed, we put drift velocity, VD, and VD, drift to the side. Drift velocity, we call it. Okay. So this is the road to get. You know this, right? You learned this in AS. Recall back. Current is what? Number of charge density times the charge times the area times the drift velocity, right? Yeah, that's your current, NEAVD. The N is the density charge of the article of the metal. A is what? A is the width times D. Area, uh, area, W, oh, sorry. Yeah, W times D is your area, this cross-sectional area, The area is at this side one, this area to be used. Correct? The current flow, NEQA, the A is a cross-sectional area, right? Cross-sectional area of the current, right? You see the current is flowing up to down. This small area is the one to be used for the current. This area. So this area is what? W times D. So A is W times D. So you put the W times D inside. Okay, sorry, W times D. So magnetic force is what? Become like this. What is your original magnetic force formula? Magnetic force formula is what? B QV. B Q we put E. V is, yes, the drift velocity. Drift velocity, can you get it from here? What is drift velocity? Drift velocity is I over NEA, correct? I over NEA. That's why you get this formula. BEI, actually EIB, same over NEA. How they get this formula? You substitute the drift velocity in terms of I over NEA. N is charge density, E is the elementary charge, A is the cross-sectional area. Okay, so this is the magnetic force. At equilibrium, achieved, the magnetic force must be equal to the electrical force. Okay, what is the electrical force formula? Electric force, what's the formula? So AS knowledge again. QE, right? Q times E, right? Q times E is what? E is, the V over D, your voltage divided by the plate separation. So QV over D, your electric force. QV over D. In this case, the Q is the E, put elementary charge. V is the whole voltage. D is the plate separation. Okay. But in this case, where's the plate separation? I go back to the diagram. Which is your plate separation? Where's your parallel plate? Parallel plate is the side one, the side one is the parallel plate. So the plate, the side one, the side plate separated by what? Separated by W. W is your D, your plate separation. Okay, so D is actually EVH. Your D is actually the W, the plate separation. So this is your force, electric force. So this is your electric force. VHE over W is electric force. EIB over NEA is your magnetic force. These two forces equal. Then you get this. You guys, come on. Equate these two. You won't directly get this. You must change something. Think for 1 minute. These two equate. Can you show it become like this? Let me see. VHE over W is equals to EIB over NEA. I make VH as a subject. So VH as a subject. EE was cancelled. W goes up. It becomes WIB over NEA. But you see this formula? W is not there. W is not there. Down got NE. Here also got down got NE. But down here got A, here got D. So what happened? What has been substituted? The area. The area is actually what? Can you write area in terms of W? Area is what? Up here, you see? Area is what? Area is what? A equals to W over WD1, W times T. Go to the diagram. Huh? The site area equals to what? The W times the thickness D. So what they did? Up is WIB, down is NEA, this is WD. So that substitution you have to show. So WW cancel, you get this whole voltage formula. Here you get this whole voltage formula. Okay. Whole voltage. But as long as the others remain constant, I NEA must NED must be remains constant. Okay, but this lots of questions have been asked from this formula. Okay, you see here, the whole voltage normally will be millivolt. Okay, to be very millivolt, very small. So it's important to have a very significant whole voltage. To get a big whole voltage, to get a big whole voltage, how do you use the slice? Must be thick or thin, must be long or short. You have to find out that. You see, to get a big whole voltage, these are the factors affects the whole voltage, I, B, and E, D. You want to get a big whole voltage means the magnetic field must be big. We can't control that. We want to calculate the magnetic field. So B, we can't control. Current, we can make the current big but dangerous. So the current also we make it small. The other two we can do. To get a significant big whole voltage, we can play around with the N and D. To get a big whole voltage, you must use a material with a high N or small n. Yeah, you want to get a big whole voltage means you must use a high N or small n. A material with a high charge density or small charge density to get a big whole voltage. The N must be small, right? The N must be small, okay, to get a big significant whole voltage. Because normally whole voltage is very, very small. To get a significant whole voltage, we make sure the material we use has a very low N, very low charge density. That means tell me, the whole probe must be made of a slice of metal or semiconductor. This plate, what is suitable to made of a metal or a semiconductor? Which is more suitable material, metal or semiconductor? Anybody? Metal or semiconductor? You see the whole voltage? You want to get a big whole voltage, the N must be small. To have a very small N, the plate must be made of metal or semiconductor. Which has a greater N? Metal has a greater N or semiconductor has a greater N? What is N? Charge, the number of charge carriers per unit volume. Charge density, yeah, we call it, charge density. Which has a greater charge density? Metal or semiconductor?
Metal.
Metal as a semiconductor. So here you want N big or small? You want N to be small. Why you want the N to be small? Because the equation tells small N can leads you a big whole voltage. You want to get significant whole voltage. So normally the whole probe, we call it whole probe, development of whole probe. The whole probe made of semiconductor. In exam they will ask, why the whole probe made of semiconductor? So what is the answer you're going to say? Because to have a significant whole voltage value, the whole voltage is found to be inversely proportional to the charge density. To get a significant whole voltage value, the charge density must be quite low. Therefore, semiconductor is used. Okay, so that's about N. You want to use a smaller N so that VH is big. Next, another one thing we can control is D. Okay, what is D? D is the thickness of the plate. Use small d or thicker d, greater thickness or smaller thickness. Use a smaller thickness or greater thickness. Use a smaller thickness, right? Smaller thickness, greater d. That's why in hole voltage, in hole probe, they use a semiconductor. The thickness of the slice will be very thin. Use a thin thickness. Remember, the dimension, the length dimension in hole voltage is actually that dimension, the length dimension is parallel to the magnetic field. You see, the magnetic field is upwards. You have three dimensions: the vertical thickness, the horizontal length, then the cross section, the width. The distance you must use is the distance which is parallel to the magnetic field strength. And if it's up, that is the thickness will involve in the formula, the D. Okay. Okay, so to have a good hole probe, you use a semiconductor and use a smaller thickness to have a significant hole voltage. Okay, so that's about hole voltage. Any questions, guys? It's something new. So we go back again. I show you what is meant by hole voltage. Magnetic field create electric field. The magnetic force, electric force balance each other, causes the hole voltage created at the site. Okay. By using the derivation, the drift current formula involving drift velocity, magnetic force, the drift velocity has been replaced. Electric force and magnetic force is compared equal, and we found that drift the hole voltage found to be IB over NED, and this helps us to discover what type of material and the dimension to be used to measure hole voltage, therefore can lead to calculate the B. Okay, so yeah, so VH found to be proportional to B. This could be a 3 marks question or 3 or 4 marks question if comes out in exam. Derive. You have to know the derivation. Okay, guys. Any questions? No questions. Good idea? Okay. So I don't want to track further. A lot of information you learned today. So I'm going to stop here. In next class, we discuss about the velocity selector. Okay, so what you learned today? Okay, what you learned today? A small recap. So you learn about current balance, the way finding the magnetic field strength. Moment is used to measure the magnetic field strength. Then we talk about force on a moving charge. F equals to BQV. And we found that the charge moves in a circular path. Reason you have to know. The force is always perpendicular to the direction of motion. Therefore, it's in a circular path. Then the R formula. Very, very important development for nuclear science to discuss, to investigate about the property of particles. Then finally, we talk about what is meant by hole voltage. Okay. And hole voltage, how it was derived and led to VH equals to IB. Okay. Remember in these notes, the important things is missing is when you equate these two. The EIB over NEA equals to VHE over W. We make what? VH as a subject. We got WIB over NEA. E cancels. Okay, then what do we do? The W has been substituted. W has been substituted as what? Sorry, the A is substituted, and the A is substituted as WD. So WIB, NE, WD, W cancel, you get this formula. Okay. So conclusion, VH is found to be proportional to B. Okay. Okay. The Hall probe normally will give you in millivolt. it gives you volt. It won't give you directly Tesla. It gives you voltage. So when you purchase a Hall probe, it will give you in a millivolt. So you put, how are you going to measure? How do you want to get the magnetic field in terms of Tesla? So to get Tesla, you need to calibrate this Hall probe. How do you calibrate it? Bring this Hall probe close to a known magnetic field, maybe MRI. Okay, MRI, 3 Tesla. So you bring this Hall probe near to the MRI. When you place Hall probe, remember when you place Hall probe, the Hall probe surface is like this. This is the semiconductor, you know. Make sure the magnetic field is like what? Magnetic field is 90 degrees to the, or normal to the surface of the Hall probe. Okay. So how do you do that? You have to turn around now. You turn around. You turn around the, what do you call, the Hall probe horizontally until the millivolt gives you the maximum value. And when the millivolt gives the maximum value, we understood the magnetic field is already perpendicular to the surface. So if the MRI is 3 Tesla and your millivolt, you got 3 millivolt. Okay, we already calibrated 3 millivolt, 3 Tesla. Now you bring this Hall probe to an unknown magnetic field strength and you got 2 millivolt. Understood, right? How many Tesla is this? 2 Tesla. Proportional, because VH is proportional to B. So we calibrate first. Then you get the Tesla. Okay, so yeah, that's for today's lesson. Okay, any questions? Okay, no questions. Okay, so for tomorrow, it will be a practical. We're going to discuss practical for the first time. Okay, I'm going to give you a video for you to watch, and you need to do the first experiment for me. You must draw the graph and everything. We'll be discussing tomorrow. Okay, so the practical book, the practical book I already attached in the times. So go to the practical, go to the A2 practical set 3. A2 practical set 3. So you open up A2 practical set 3 here. Okay, so the experiment C, D, F, we will be discussing the analysis question, C first. The video is about the C. I'll show you the video. So tomorrow, I want you to do the C1. I want you to do the C1. Look at the video. Okay, the video, the seniors lesson, you read it. It's going to be about the same. Look at the video, what I'm saying. Try to get this data. Try to do these questions. And try to plot this graph. Okay, this is homework for you today. After you watch the video. Okay. After you've done this, and I want you to submit this graph through WhatsApp. Okay. Before next class, Friday, before 2 o'clock, maybe tomorrow. Yeah, I want you to submit just this graph only after you draw. Okay. After you watch the video. Wrong, never mind. Just give a try. C1, C1.
Where will the video be?
The video I post it in WhatsApp now. Actually, the video is here. The video is hold on. So this is your practical set 3. You must do C1. Video, you go down. Go to the AS online classes, right? At the bottom. This is AS practical. I want an A2 practical discussion. Yeah, you see the A2 practical analysis question discussion. This one, 23/7, A2 practical analysis question discussion. Okay, this video. I'll post it on the WhatsApp. I'll post it on the WhatsApp for you to easier for you to watch. Okay, you watch this. It's under, actually it's under AS online classes lah. Go towards down. Okay, where is it? 23/7. AS practical analysis question. Open up this. If I open up this, you can see the video. Watch that. Go back to your set 3. Go back to your set 3. Okay, A2 practical set 3. Do C1. Okay, do C1. Okay, C1 experiment. So tomorrow I'll see you with, you are completed the C1. Okay, after you watch the video today. Send me the graph by tomorrow 2 o'clock. Okay, any questions? Hope you understand. Okay, another one thing. I marked your tutorial, the quiz already marked. You can check your results. Okay, I put the answers for the quiz too. Okay, there is a common mistake I come across. The common mistake is about the term angular frequency. What is meant by angular frequency? Angular frequency is not finding frequency. Angular frequency is actually omega. You know angular velocity? Angular velocity and angular frequency sharing the same formula, omega. Okay, some of you wrote angular frequency, you calculated frequency. Hertz, wrong. Angular frequency is radian per second, omega. Omega is angular frequency. Angular frequency is used in oscillations. How many radian it covers in a second. They never call it as angular velocity. Okay, they call it angular frequency. Angular frequency means omega lah. I remember omega. That's a common mistake I've come across here. Okay, check your quiz. Yeah. Any questions, guys? Okay, so see you tomorrow with your practical. Tomorrow we'll be doing 1 hour practical. We discuss about the practical. Any questions? No questions. Okay then. See you then. See you tomorrow.